In this tutorial, we are going to go over creating a physics thorn within Cactus. Our thorn is going to implement the Maxwell system of equations, and we'll talk about exactly how, the design choices we're going to make there, and then some implementation details. The actual work required to create this thorn would require much longer than the time we have allotted. So I'm going to go over the choices that we make and the implementation details. To to follow along with the code, please look at please go to the following Bitbucket page, and you will see instructions for how you actually should be downloading this code. And basically, what I'm assuming is that you're going to be in some kind. You will have download the Einstein toolkit, and then you'll have some directory. For example, the way I have it, I have a directory where where I've run get components and I have Cactus, and you just in that same directory you run this command. I won't be able to run this because I can run. I just will hit no when it asks me to update. Okay, and it will download the repository, which contains the thorn from this tutorial, as well as the actual notebooks that I'm going to be using in the tutorial. And if we go into Cactus, once you've run that command, and repos, and tutorial, you will see the Maxwell thorn over here, another older wave equation thorn, we're not going to worry about that, a notebook directory, which contains the notebooks that I'm going to be discussing here, and as well as some configuration file information, including a thorn list and a Cactus configuration file, which I found to be useful for CentOS 8. Okay. Okay, I'll come back to the code in the second half of this tutorial. At this point, I would like to first talk about the system we want to implement. So we are going to be implementing the Maxwell's equation. Well, I should say not quite Maxwell's. It's an augmented Maxwell's equation. We're going to Maxwell's equation with source. So we're going to our evolve variable are going to be the electric displacement, the magnetic field B, the free charge density rho, and also two auxiliary fields, psi D and psi B. And we'll talk a little bit about those two auxiliary fields later. Notice that if psi D equals psi B equals 0, we reduce to the Maxwell system. If psi B and psi D are not 0, it turns out that this is going to have some advantages, which we're going to see just a little bit later on. And we're going to be assuming that the free current density is going to be given by some spatial function sigma times the electric field. The electric field is going to be given by the electric displacement divided by some specified function epsilon, and the H field is given by the B field over mu. And we're going to make the requirements that sigma is greater than 0, epsilon and mu are greater than or equal to 1. Now, this implements the evolution part of the Maxwell's equation. There are, in addition to that, constraint equations. Del dot D has got to be equal to 0, and del dot B, has got to be equal to 0, and del dot D has got to be equal to 4 pi rho free. And we'll call del dot B CB and del dot D minus 4 pi rho CD. Okay? And if you plug this into the above evolution equations, you find that CD and CB obey the following damped wave equation. So if we have constraint violations, what happens is the CD and CB, if they're non-zero, they start to move towards 0 with this damping constants, either KD or KB. And so basically what happens is that if our evolution takes our system off the constraint surface, in other words, del dot B and del dot D is no longer have the appropriate values, then what happens is that constraint violation will get damped away. Okay, and we'll get back to this later, but the way you can think of most generally how our system is going to look is we have a bunch of variables whose time derivatives we know, and we want to integrate these time derivative equations. Of course, in addition to time derivatives, we also have spatial derivatives. We have all the derivatives associated with the curl and with the divergence and with the gradient. So we're going to have to figure out how to actually first implement spatial derivatives. And so let's get to that first. Okay, so let's start with something really simple now. Suppose that we have some function f that we want to store on our cactus grid, and we also want to store on the grid the gradient of f. So we want to store f, its x derivative, y derivative, and z derivatives. Okay, so in order to allocate storage for that and to tell Cactus about these arrays, in our interface.ccl file, we are going to define a group which will just contain, in this case, one entry, one element, and that'll be our field f. It'll be a grid function. For no particular good reason, I said that has 3 time levels. I'll always do that if we have an evolved quantity. If it's not evolved, it doesn't. We probably should choose that to be 1 rather than 3. And we're telling also that Cactus that it is a scalar variable. This is going to be important when we want to apply symmetry boundary conditions. And we have another group, which I'm calling my gradient, which is going to store the 3 fields for the gradient. And we're telling Cactus that this is in fact U is a symbol for a vector. This is a vector. And that's going to be really important, again, for our symmetry boundary conditions. Because scalar, so for example, if we have a symmetry boundary condition which is a reflection, scalar fields under reflection behave different from vector fields under reflections. Okay. At this point, we've told Cactus that we have these 4 fields. In our schedule file, we will have to tell Cactus also that we want to provide storage. And notice that we tell it we want to provide storage for the group name, that's this name, not for the individual fields. Okay. Now that we've basically talked about how you tell Cactus how to define a grid function, we have to see how we actually use it. Because Cactus stores our 3-dimensional array, our 3-dimensional grid function, as if it was a 1-dimensional array in Fortran ordering. So we want to compare our logical indices, I, J, K, representing a position in X, Y, and Z, with how it's actually, where the data is actually located on the array. And the indices go like this, as we go from 0 to 1, I goes from 0 to 1, and then to 2, and so on. And notice that as we move around down the array, I is changing, but not J and K. At a certain point, we run out of all the I values that we can put on here. So we're going to get to nx. So if there's nx elements in the I direction, then the last element is going to be nx minus 1. Okay, so we come up to array index nx minus 1. We have, that's the logical index. Then we have optional padding. So the next index in the array might not represent anything physical. This padding could be of size 0 or not. After the padding, there's going to be another element later on, which is going to now contain the very next data point, which is going to be actually when j switches from 0 to 1. So notice we're back to I equals 0, and k remains 0 the whole time. This process repeats. I is going to increase, and then more slowly j is going to replace, and eventually we get to this point here, where we filled in, we're at the nx minus 1 and ny minus 1 elements. And then after some more padding, the next element up is going to be element 0, 0, 1. And then this process completes until you finally have all of the array indices for all of the possible IJK elements. Now, we don't have to worry about the mapping between our logical index IJK and the array index. That Cactus handles for us in this macro cctkgf index 3D. It takes its arguments. Oops, I did not mean to do that. It takes as arguments, my apologies, it takes as arguments cctkgh, that's this critical Cactus structure which most Cactus functions are going to have passed to them, and then the ijk indices that we want. So for example, if we want to find a value of our array at logical index ijk, we would just use that syntax in C. Okay. So let's start to use this to actually generate those derivatives. So first thing is, if we're going to calculate a derivative, we need to know the grid spacing. And the grid spacing is going to be given in CCTK delta space. So you notice that it's parentheses 0, and that's actually should have been 1 and 2. That is a mistake. I will fix that right now. Okay, with that fixed, we can see we can get the x spacing, the y spacing, and the z spacing. Now what we also have to keep track of is the stride. So if we want to move 1 unit in the I direction, we need to know the stride, how close, a particular ijk is from I plus 1 jk. And that stride is going to be given exactly by the distance in our array when we go from element 1, 0, 0 to element 0, 0, 0. And the stride in y is going to be very similar, except we're moving 1 unit in the j direction, and finally 1 unit in the k direction. So let's see how the derivative looks. To get an x derivative, we're going to move over 1 unit in I in the plus direction, 1 unit in I in the minus direction, and then we're going to divide by twice the spacing. And to get the y derivative, again, we do the same thing, except we're moving 1 unit in the j direction, in either up or down, and finally 1 unit in the k direction. Notice how these derivatives all look very similar. It's the stride which tells you if it's going to be an x derivative, a y derivative, or a z derivative. We'll make use of that later on in order to define macros which handle the derivatives and basically are completely agnostic as to which direction they're actually taking the derivative of. Okay. One other thing which I note here is the loop bounds. So k goes from 1 to this CCTK LSH2 minus 1. The actual allowed values of k are 0 through CCTK LSH2 minus 1. So in other words, LSH actually contains the dimension of the array, of our array. So LSH0 would be the x dimension, again the y dimension, and then the z dimension. Now we are skipping one point in both the left and the right because we can't go to index, we can't go from index, we can't have a negative index value or an index value that's too large. So let's say I was 0. If we allow I to be 0 and we subtract di, we're going to what's effectively a negative I, which is not even on the grid. So we're going to be looking at the wrong area of memory. So we have to restrict ourselves to dropping 1 point on the lower end and 1 point on the upper end in each direction. If this was a higher order derivative, we would have to drop more points. Okay, so let's talk a little bit about some of the design choices we're going to be making through this code. And so for our interior and boundary algorithms, we're going to be using various finite different operators. We're going to have more or less the same algorithm, just implemented with different order operators. And rather than rewriting having a bunch of almost identically repeated code, what we're going to do is implement our main algorithm in terms of macros, and those macros will be calling other macros. And I'm going to show you an example of how this is done here. We have a very simple algorithm here. We have our macro called main algorithm, and all it does is it calculates, it says that dxf at some index is equal to some other macro operating on f. And similar for dy and dz, which as it stands right now does virtually nothing useful. But we're going to continue. We have some more macros which we're going to define. We have this macro here, and I don't want to go into the details here, but this macro will calculate a second derivative. It basically will take as input an index, so not ijk, not I, or it'll take an actual array index, so not the I, j, or k, but the index thing that we have over here. a stride, it's called di here, but it could be either di, dj, or dk, and a spacing. And it will yield the derivative. And then we do something very similar for the fourth derivative. It just looks a little bit more complicated. Now finally, I define that this diff x macro, let this diff x macro be the second order derivative, second order x derivative. So the stride will be a di, the grid spacing will be dx. The y1 will be, so diff y is going to give you the y derivative, because we can see that where the stride is dj and the spacing is dy, and similar for the z derivative. This particular macro, for no particularly good reason, assumes that something called OO2 dx, dy, and dz are defined, and that just stands for 1 over 2 dx and 1 over 2 dy. So I just define that. Now I have my loop, and I have to define my index, and later on in the code I'm just going to use ijk for the index. And then I have my macro main algorithm. Okay, and then I said, okay, well, I don't really want second order derivatives. I want fourth order derivatives. So I just basically do the same thing. I just define diff x, y, and z to be the fourth order derivative. And again, I have the main algorithm again. I take what I have up here and I plug it in with the C preprocessor, and I get the following code snippet. And if you look here, other than it's a little bit cluttered with parentheses, but you can see here that I have second order derivatives. And then later on, other than the little bit of a different formatting than what I was expecting, but we basically also have fourth order derivatives. And so at this point, it doesn't look all that useful because we could have just as easily just typed in, rather than typing in main algorithm, we could have just typed in this in the both places, and it would have been more readable just to type in dxf equals something from a macro dy, something from macro. But we're going to see that this algorithm is going to become sufficiently complicated that it actually is going to be worth our while to implement it and debug it once and just use a macro for every other subsequent use of that. Okay. And so that's going to be one of our design choices, and it will have some advantages and have some disadvantages. And one of the disadvantages is going to be it's going to make following the logic of the code more difficult. Okay. Another choice that we're going to be making here has to do with the outer boundary conditions. Now we can play with this thorn quite a bit without any boundary conditions, just by imposing, for example, periodic boundary conditions. But if we want to actually have outer boundary conditions, we have to really think about that. And the way we're going to actually deal with it is we're dealing with ultimately a hyperbolic system, a system which can be written in this form. And we are going to apply the boundary conditions not on the function u, or the source term u, not the solution vector, the solutions u, but on their actual time derivatives. Okay, and you'll see how that happens in the next Python notebook. Okay, so I already showed you this notebook before. I'm going to show now. We're going to go into the details here. Now, this particular Jupyter notebook, unlike the other one, doesn't just have comments on it. This actually has code here, and what the code actually will do is we'll actually implement the macros for the interior algorithm and the boundary algorithm. For convenience, if you look at these equations here, notice that D and B are the evolved variables, but they don't show up here. So we have H that actually shows up. H is B over mu, and E is D over epsilon. So it turns out it's going to be convenient to define grid functions not for epsilon, but for something I call I-eps, which is 1 over epsilon, and I-mu, which is 1 over mu. Sigma appears in the numerator, so we just keep sigma the same. Now, again, what we have now, our system of equations is just the time derivative of some vector is equal to spatial derivatives of that vector. And plus source terms. And what we're going to, in order to analyze the boundary conditions, what we're interested in is going to be what happens if we take, so what happens if we actually ignore all derivatives which are not normal to the boundary. So we're going to ignore every term which is not differentiated, and we're going to ignore every term which is not whose derivative is not normal to the boundary. And we write this system in this form: dt of the solution vector is equal to some matrix operating on the normal derivative of u. Okay, and this c would just be, we originally had in the previous case, we wrote these three matrices, ax, ay, az. If you kind of combine that into a super vector and you dot that in with the normal, then you're going to get this C matrix that I have over here. Okay. The interesting thing is going to be this C matrix, and in particular its eigenvectors and eigenvalues. Now suppose that V is an eigenvector of C with eigenvalue lambda. What we have is that if we take our solution vector U and we dot it into our V lambda, and we look at its evolution equation, we're going to see that dtu lambda is equal to lambda dn u lambda. And that's an advection equation. And so basically, and that means that we're going to have fields moving at a speed of, in this case, it's going to be minus lambda. And so what that means is that we're going to have some solutions, some u lambdas, which are moving into our domain, and some u lambdas which are moving out of our domain. And the way you construct proper boundary conditions, or somewhat proper boundary conditions, we're not being really perfect here, is that you apply boundary conditions on fields which are coming into the domain. You choose whatever you want. We're going to choose that their time derivative is 0. And fields going out of the domain, the time derivative is going to be set by the internal algorithm. So in other words, if let's say if u lambda represented an outgoing field, we would say the time derivative of u lambda is just the interior algorithm's time derivative of u dotted into v lambda. And the way this is going to work is u lambda is going to be some linear combination of the regular u's, and there'll be a corresponding other value of lambda where there'll be two, basically, there'll be two different u lambdas, and they will basically contain appropriate linear combinations of a given field so that we can determine all the actual time derivatives of u. It's either going to be through the interior, some combination of interior algorithm and some combination of setting right-hand sides to 0. Okay, and just if you want to follow along on the notebook below, this is the actual vector u. It's just going to be it's just the b's, the d's, and the psi's. I actually forgot the rows; they're there as well. Although I do drop row when I try to actually generate the boundary conditions. Okay. The rest of this notebook is simply going to actually construct the interior algorithm and the boundary algorithm. So I am using SymPy to do most of the heavy lifting, and there's going to be a talk right after this one where on the NERPy code, which automates a lot of what I'm doing below. And because what I'm going to generate here, what I'm going to use here just generates macros. It doesn't generate full codes or anything like that. Okay. And I'm just defining some functions, the dx, dy, dz, bx, by, and so on, telling what the h vector is, what the e vector is, what the j vector is. And these are my evolution equations in this syntax. B dot is the minus the curl of the e vector plus the gradient of psi b. B dot is the curl of the h vector, gradient psi d minus 4 pi j. And psi b dot and psi d dot, you can see that those are the divergence of b and d minus your kappas. And for the d dot, we have the also minus 4 pi rho. Okay. We also need, as I kind of just briefly mentioned above, we also need the evolution equations where we drop all the source terms and all the non-normal derivatives, and that's happening here. There's a bunch of replacements that I kind of just, I'm not a Python expert. I just kind of made some manipulations until things actually worked. And I'm going to skip most of this just to show you basically at a certain point, we start to produce the actual macros. So kind of do figure out how many derivatives we need, and we construct all the derivative names. And then all the time derivatives are filled in here. So those are spatial derivatives. These are all the time derivatives. And then something similar again for the boundary conditions. It's just a little bit more complicated. Now, if I run this, it will produce a header file, and it will also, if you have Clang format, this will, if you don't know, this will error out. But if you do, this will actually clean up the header files a little bit. And I'm just going to show you what they look like. Okay, so this is the header file. It's been cleaned up a little bit. Let's get to the beginning. This derivs macro just defines all the derivatives. So it just says dx/bx is the x derivative on bx and so on. And then we have the interior algorithm, which fills in the derivatives, and then actually fills in the right-hand sides. And for example, you can see here for the bx equation, we have a gradient of side B, you can see there, and also dy dz, and then minus dz dy, or I got the signs wrong, but that looks like a curl operation. Something similar is happening for the d, and you can see that for the psi's. You can see here there's a divergence, and maybe I'll just make that a little bigger so you can see it. Here's a divergence, and for the psi d, you can see a divergence and then also a row showing up. I also defined derivatives for the boundary conditions. This is just, there are fewer derivatives that we take on the boundary, and rather than having the compiler complain about unused variables, I just defined the new macro so that there's just fewer that are defined. And these are the boundary conditions, and again, we just have a different right-hand side for each of the evolved fields, but we have also boundary conditions in the x, upper x, lower x, upper y, lower y, upper z, lower z. Don't have to worry about the details there. Those have all been set in this particular notebook. Okay, so let's actually start to go through constructing this thorn. Okay, so the first thing we want to construct is an interface. This is going to tell Cactus what variables we have and how our thorn interacts with other thorns. So first thing is we have to tell it that our thorn has a name. We're going to call it simple Maxwell. And it depends on the grid. So it needs to know about the grid. And now we can define evolution variables. And we can see here that we have what I call evolve vector d. That's the d field. And you can see dx, dy, dz just coming there. We have an evolve vector v field, and it's bx, by, bz. Notice that both of these are of type vector. We also have to define variables which are going to hold the time derivative of each one of these fields. So time derivative of the d field, and this is also itself a vector. It turns out we don't need to checkpoint that, so we also can tell it not to checkpoint. And we're not going to need more than one time level for that, so we can set the time levels to 1. And then we have the evolve, the vector fields, the fields that store the time for the time derivative of b. We next have the 3 scalar fields. They're type scalar, and those are psi d, psi b, and rho, and storage for their time derivatives. And we have our constraints cb and cd. And finally, we have 3 other fields. These are, I call them static fields because they don't change. Those are the sigma, the epsilon, and the mu, or in this case, sigma 1 over epsilon and 1 over mu. In addition to that, we need a bunch of standard boilerplate code. We need alias functions from mul. We need alias functions from the boundaries. Just cut and paste that stuff into your new thorns is my suggestion. Okay. Our thorn is also going to require parameters. So we're going to have our kappa B and our kappa D. Um, and we know they have to be positive. And so the syntax here, yeah, first of all, we say that this is the magnitude of the constraint dissipation. It's positive. Um, and we set some default value. In this case, it's going to be 0. This steerable argument allows us to change it if we want when we can stop the run and restart it with a different value of kappa if we choose to. Okay. The next thing that we're going to have is a parameter which just describes initial data, and it's not H, it's B. And I'm just using keywords here. These are just particular choices that I made when I wrote this thorn. We'll see about that later on. And then the I epsilon, the sigma, and the mu, I call those material properties. And I have some options. They could be constants, or I had some I call 2 blocks, where basically we just have 2 blocks of material, and we can choose the properties of the blocks of material. And I would encourage you to consider other sources, other material properties as well. And then we have some more parameters which just describe these options. You know, your constant mu, constant epsilon, constant sigma. One choice that I made here is that although the variable that I store is the reciprocal of mu and epsilon, I actually specify the actual values of mu and epsilon here. One other option is it says set row from D. If you just give arbitrary initial conditions for the D field, you will have constraint violations because del.d will not be equal to 4 pi rho. This option just recalculates rho based on D. And then I talked about the 2 blocks, and this just determines the geometry of the blocks and how wide the transitions are. So the blocks are smoothly, basically there's it doesn't represent quite a square function. In other words, it's not like epsilon is 1, and then inside the block epsilon is exactly 2, and it doesn't jump there. It tries to smoothly go, make a smooth transition. Okay, and basically those parameters just determine the material properties. And you see that most of the complication is on things which we haven't really discussed. It has to deal with, do we want to make sigma, epsilon, and mu less trivial? Okay. If sigma and epsilon and mu were trivial, then all we would really need is just kappa B and kappa D. Everything else would be unimportant here. And that's basically kind of the way these thorns go, as they do tend to grow in complexity. Okay. There is a file called configuration.ccl, which in this case is empty. We don't need to worry about it. And finally, we have the schedule file. So schedule file, I mentioned before that we tell Cactus about what storage we need, but we also have to tell Cactus when to run various routines. So all our time integration is going to be done through this method of lines thorn, and so we have to tell the method of lines thorn what variables we have and how they're going to be evolved. And so we have to make a routine called simple maxwell, a routine that we run in this mul register time bin that will actually tell mul, hey, it got these variables. And then we have another routine which we're going to have to create, which runs on the initial time in order to actually fill in all our initial conditions. And then we can see here an option. If we have that option, that parameter we had before, set row from D, if that was true, then we're going to call another routine which actually does the operation set row from D. We're going to call it initial after we've initialized. So we've initialized everything. We have a D and a row which are inconsistent, and then we rewrite the row. Okay. And you might also notice these things, options global, options local. That's going to be important when we have AMR. Okay. So when we're directly writing to grid functions, we want options local. Generally speaking, if you're not doing that, you probably want options global. Okay. And we have one more thing here. Set row from D involves taking derivatives. So derivatives, if you're taking derivatives, that means that there are some ghost zones at the processor edges. What this synchronization does is this will synchronize those ghost zones after this routine is completed. Okay. Well, if we have an evolution system, we have to fill in the right-hand sides. And so we do that in simple Maxwell right-hand side. And so we have this interior algorithm. And basically what a schedule group is, it just allows you to combine a bunch of different functions, the scheduling of a bunch of functions together. It allows you to keep them together, and also allows you to get the logic, to simplify the logic and making sure that if, let's say, one routine has to come after 5 different routines, rather than saying this has to come after all 5, you can just put those routines in one bin and say it's got to happen, the dependent function has to happen after that bin. So we have our interior algorithm, which is going to be in the right-hand side. And then for the way that I'm actually doing this, we need not just the right-hand side and the interior, but the right-hand side I call near boundary. And it has to do with the way that we're actually going to be implementing the boundaries. And that is, we're going to do 4th order accurate in the interior, 2nd order accurate 1 point away from the boundary, and 1st order accurate on the boundary itself. Okay. So simple right-hand side near boundary is going to implement the exact same algorithm as simple right-hand side interior. It's just going to be with 2nd order accurate operators and over fewer points. Okay. Once we've handled the right-hand side near the boundary, we can handle the right-hand side on the faces. This is actually going to be our first time where we're using a true boundary condition. Once we've done the faces, we can do the edges. Once we do the edges, we can do the corners. And then we are done filling in the right-hand side. But one thing that we haven't dealt with is, what if we have a symmetry boundary condition? So if we have a symmetry boundary condition, for example, you have reflection symmetry about the xy plane. Well, we have to handle that as well. And mostly this is going to be standard boilerplate stuff. We're going to schedule a boundary. We're going to schedule a routine which does very little. It's called simple Maxwell boundaries, which makes it sound like it does a lot, but it does very little there. We're just going to schedule that and post mini step. It turns out the way this works, it has to be in level mode, which is a different mode, kind of between local and global. And we're going to be synchronizing our variables at that point once this is done. And then we actually have to apply the boundary conditions. Again, these are only symmetry boundary conditions. And we do the same thing, but just in a few other bins. I don't know if this is necessary or not. Okay. And then we also have to evolve the constraints, or evaluate the constraints. And there's a special bin for constraints that's mul pseudo evolution. And so we have the constraints, but we also have boundaries associated with the constraints. So there's, again, a little bit of a repeat. And we have to set up the epsilon, the mu, and the sigma. And that actually cannot be done in initial. And the reason why it can't be done in initial is because you need initial is only called at the beginning of a simulation. You might have a simulation which is continuing. So you need to make sure that the constant fields are set up even if you're continuing a simulation. So it's done in a different bin. Okay. Also, if you have AMR, you have to reset those constant fields as well. And there might be a good reason why you want to have AMR, especially if you want to follow an interesting type of wave pattern. Well, that's, the schedule file tends to be some of the most complicated part of the whole code. Let's go into the actual source directory and see how some of these things are actually implemented. The first thing I want to look at is mul register. Okay, And because the syntax is pretty straightforward. Basically, we tell mul that we have a variable, in this case the dx variable, and its time derivative is stored in that variable. And we just do it for all the evolved variables. We also do it for the constrained variables. And that's it. We have now told mul exactly how to evolve all these variables. Of course, mul is assuming that we are going to fill in .dx, .dy, .dz, and so on and so forth. Okay. I want to look at the next one I want to look at is sim boundary. And this handles those symmetry boundary conditions. Those are the two functions which were called in apply bound, called just above here. So the function's called in level mode. Okay. And what you can see is they don't do very much. All they do is they just say, hey, next time it's available, please apply boundary condition to D, B, and the scalars. And in the constraint boundaries, just next time available, please apply boundary conditions for the constraint scalars. So that doesn't do very much, but it has to be called. Okay. And let's look at the interior. Okay, so this is the main interior algorithm. Here's kind of a standard way that a standard cactus function. We have, just a function that returns void, and it takes as arguments cctk arguments. And you have to include cctk.h, arguments.h, and parameters.h. And then you have to declare cctk arguments and parameters. Well, technically, you only have to declare parameters if you want to use them. Okay. This should be an unnecessary step. But what I'm doing here is I'm zeroing out all the functions before I write to them. Okay. And then the following should look very similar to what we've seen already in the notebook. We had to define this 0012dx. We got the di, the dj, the dk. I need to define a ghost size. I have to define diff(x), diff(y), diff(c). One other thing I added is just really trivial OpenMP parallelization, which is just adding that one line. And k, you can see rather than saying k equals 1, k less than or k equal 2, k less than cctk lsh2 minus 2, etc. I just call stencil ghost. Just use a macro stencil ghost and just set it to be the appropriate one. At that point, I then just call simple maxwell interior, not call it, but I have the simple maxwell interior dot macro. And this dissipation stuff was supposed to be removed. I will actually do that right now. Okay. And let's see what this is. We have actually already looked at that. That was in simple macro.h, and it's right here. This is what it actually does. So first of all, it fills in all the derivatives. That's all this stuff over here. And then we're filling in the right-hand side everywhere. Well, so the right-hand side for all the variables. We continue on. We have right-hand side near boundary, which is basically identical to the right-hand side in the interior, except we're going to be using second-order accurate stencils. So our ghost size is going to be 1. But also, we only apply this when we're near the boundary. So cctk box 0 is going to be true if the lower x boundary is of our processor boundary is actually the lower x boundary itself. And so if we're on the lower x boundary, we're just going to the only thing we're missing is this interior algorithm evaluated second order on the lower x face. And it might also be on the upper x face, the lower y face, the upper y face, lower z face, upper z face. Okay? So it looks more complicated, but it's basically the exact same thing, just being called in different loops. And you see just a huge amount of code reuse. So that's one of the things where it makes this macro really nice. The other thing is that we can switch between derivative orders pretty simply. Okay. By far the most complicated thing in this code is the actual boundary condition. And probably, so let's just look at faces. So boundary condition on faces. So if we're on the lower x face, I is going to be 0. That's always in the lower x face. And we are, our stencil size is going to be, our ghost size is going to be 1. And what you see here is that any derivative that we can take to second order we do, and otherwise we take to first order. So in the lower x face, we cannot take a centered derivative. So we have to use an upward derivative, so that we use a first order upward derivative. But in y and z, we can use centered derivatives. And then we're on the low x boundary, so that's the macro we put there. Similar for the upper x boundary. Again, now I has a different value, and now we can't use an upward pointing derivative, we have to use a downward pointing derivative. And basically the same thing happens on the y and the z faces. You then, once you have faces done, you can then do edges. And in edges, 2 of the derivatives have to be first order. And again, you have all these if statements because you have to figure out which edge you're on, because the algorithm changes edge by edge. So for example, this is the edge corresponding to low x and low y. And so we have a particular derivative we need here, and we have to say that, and we're using the low x boundary condition. This is low x and high y, and the condition I'm actually applying is still the low x boundary condition, but the derivatives have to change. And again, it just, all those options have to be filled in. And then finally, there's the corners. And the choice that I made is that if any point is attached to the low x boundary, you always use the low x boundary condition. If it's attached to the up x boundary, use the up x boundary condition. If it's not attached to either of those, but it's still a boundary point, use the low y or the up y. Okay. And at least with dissipation, that turned out to be stable. And then finally, we have to implement the constraints. And again, you can see here that, in this case, this is hand-coded. It's simple enough. I define dx, the x, y, and z derivatives of d and b, and I just take the divergence minus 4 pi rho, or just the divergence if it's depending if it's d or b, and that's it. And I'm assuming that we don't have to worry about the constraints on the boundaries itself, because basically the way this code works is that because it sets it at first zeroes out the grid function, everything, every point which is on the boundary or in the neighborhood of the boundary is going to just be filled in with 0. Okay, and finally, the final one we want to probably look at is the initial, which just basically, whoops. Either directly does something, the initial either directly manipulates the initial data, or calls a function which does that. So I have, and there's no good reason why to split that up, but that's just the way I did it. Okay, so this would be a simple choice of just a z-going wave. I have another choice here, which is an electrostatic system. And random noise, which was really useful for checking stability and debugging. And then here's that set rho from D, which just basically calculates the divergence of D and uses it to fill in rho. And again, it assumes that the divergence of D is 0 in the boundary. And here's where we're setting the constant fields. Okay, and those blocks. Okay. Well, that's it for the main code walkthrough. The next step is to actually get this thing to get it to actually run. Okay, now that we've had our Thorn set up, it's time to actually do some tests. So the first thing we want to do is we want to see if the evolution system that we coded up is stable. So I do have a Jupyter notebook here, which just all it is a listing of a parameter file. And so I just want to go over some of the basic details here. Max runtime, I think, is obvious. That's just how long it's going to run. We have to be careful for submitting a job. We have to make sure it terminates in the time that before the time that was allotted for the job is finished. There's some boilerplate things I'm going to use, and I would just suggest just copying this. Now here's my grid setup. My algorithm requires 3 ghost zones. And I'm setting it up using the domain size min and max. So I set xmin, ymin, zmin, xmax, ymax, zmax. This is a stability test. The actual scale doesn't matter, so I just set everything from -1 to 1. And my resolution is set by the number of cells. In this case, I'm just going to do 100 cube cells. This test doesn't use periodic boundary conditions. It uses the actual boundary conditions that were implemented in the code. And so the size of the boundary is 1. And this shift out, which we'll see later on in tests with periodic boundary conditions, those are just set to 0. We're going to use 4th order Runge-Kutta as our time integrator. Okay. And 4th order Runge-Kutta requires 4 steps. Again, I would just copy that. And our dt factor, that is the ratio of dt to the ratio of the time step to the spatial step, is going to be 0.5. To activate our evolution system is really simple. We just set active thorns to be simple Maxwell. In addition, it turns out that this system is going to be unstable without dissipation. Now we're going to use the dissipation thorn provided in the toolkit itself, and it happens to require these 2 other thorns. We're using a 4th order code, so we're going to use 5th order dissipation, and it turns out we need a very large dissipation of around 0.2. And I'm actually going to show you results when we actually choose a dissipation to be smaller than 0.2. The initial data is just random noise with some material. I say material, that means I don't want to just have vacuum. Epsilon equal 1, mu equal 1, sigma equals 0. So I have 2 blocks of material, and those blocks have sigma non-zero, epsilon not 1, and mu not 1. Okay, and then I have some debugging as some output. First thing is I want to check for nans in case it does blow up. And then in this case, I'm only interested in the L infinity norm of the evolve variable. In this case, I'm just outputting D. I just want to make sure it doesn't blow up. Okay. And what I'm going to do is I'm going to run this particular par file with different choices of the dissipation factor here. And I'm going to show you some results in just a moment for that. Okay, so this is the plot of the L infinity norm of dx, the other functions behave similarly, versus time. And if you look at the black curve here, and this is a log linear plot, linear log, I guess, with epsilon equal to 0, you see this very, very strong blow up here. So, the norm goes from around 2 to 1,000 very quickly. With epsilon equals 0.1, it goes slower. And then we can't see on this scale what happens when epsilon is equal to 0.2 or 0.5. I'm just going to zoom out for a second, and so you can see that these things, I had stopped the run here, that's why the black curve doesn't increase, but you can see the red curve just keeps blowing up. It gets bigger and bigger and bigger. Okay, I am going to remove the red and the black curve, and we're going to look at this again. Okay, and this is now with the epsilon is equal to 0.2 and 0.5. And what you can see here is that neither one of those shows a blow up. This is now a time scale. We're going out past 2,000 towards 2,500. And neither one actually blows up. So with dissipation, we do have stability. Okay, and we'll use that dissipation of 0.2 in the rest of our runs. Now, the next test we're going to do actually is more interesting. We're actually going to have a wave moving across the grid, and it's going to hit some blocks of material, and it's going to diffract off those blocks. Our setup is going to be we are going to have a physical boundary along the z-axis, so at z is equal to plus 15 and minus 5. But along the x and the y axes, we're just going to use periodic boundary conditions. So so the system just repeats in the y and the x directions. Okay. So our boundaries are going to be different. Our boundaries for the periodic for the x and y, the boundary size is going to be equal to our ghost size. That's going to be 3, while the z is still 1. That's the original algorithm. And if you notice here, we do need to shift out. Okay, and we need to specify using the periodic thorn that we want periodic in x and y, but not z. Evolution system is going to be the same. Dissipation is going to be the same. Time integrator is going to be the same. The initial data is going to be a little bit different, just because this is just the particular setup that I chose. Again, 2 blocks with a particular choice. In this case, I am going to choose the blocks have conductivity of 1 in these arbitrary units, but they have epsilon mu to be basically just the vacuum term, which should just be 1 for epsilon and 1 for mu. Remember, for a vacuum, sigma should be 0, but we're having sigma to be 1 on the pulse, on the blocks themselves, excuse me. And we have a compact pulse in the z direction, which is actually propagating. And we're going to put some output, and the big change here is that we're going to output using HDF5 output, and we're going to view that output with visit, and I'm going to go to that right now. Okay, so within visit, I loaded up 2 files. One of them is the file which contains the evolve vector d, and the other one contains what are called the static fields. Those would be the epsilon, the mu, and the sigma. And what I'm plotting here is a contour of sigma so that you see where the blocks are. Remember, this repeats infinitely in these 2 directions. Little bit of a bug using this. I'm using actually an XZ slice. Visit does label the axes incorrectly. This axis is the z-axis. This axis is the x-axis. So just kind of ignore the fact that it says y here. It's actually z. And what we're going to see is this wave is going to propagate. It's going to hit these 2 blocks. In particular, we're going to look at the space between them. And it's going to propagate through. And it's going to get diffracted by that. But I should just remind you that this is not a single slit. Because this is repeating, there's going to be slits over here, and so on and so forth. Okay, so let's see what happens when we run it. Okay, we see a lot of reflection from the conductive material. We see transmission through the hole. We see some diffraction waves. And we're going to get diffraction waves coming from the other holes as well, so it's going to get a little bit complicated here. There's going to be both outgoing and incoming pulses. Okay, it's about to finish. Okay, and the boundary conditions are not particularly good, so we're going to see some reflections off of them. But I'm going to stop this now. That was kind of interesting, but we can start to look at some other things. We can look at, for example, how the charges are moving. So let's actually remove the evolve vector d, and let's add a plot of the charge density. It's going to take me just a bit to actually make sure I get the right color scale. So I'll just return the video in just a second. Okay, so we're going to be looking at the same. It's the same simulation. But I'm no longer showing the wave itself, the dx field. Rather, what I'm plotting is the charge density. And so when this simulation starts, you're going to see nothing for a bit. But now we can start to see some charge building up on the edge of our conducting medium. The charge is starting to move around the conductor. And basically, the charge is going to dissipate away. Now, there are plenty of things that you can do with this thorn. You can extend the initial data to include other things. You could change the properties of the material. All kinds of things can be done to actually make the simulations more interesting. And if you want to actually explore this some more and you want some help, feel free to actually contact me. Okay, and thank you.